Imagine a complete mathematical void. No numbers, no structures, just a single abstract entity. Let's represent this as a single point, a random variable, x. Every random system has a center of mass. In probability, we call this the expectation, E of x, or simply mu. It is the unmoving anchor around which this abstract universe balances. But an anchor only tells us where the system is tethered. You can have a universe where outcomes are widely scattered, and another where they are tightly clustered, yet both share the exact same center of mass. This leaves us with a strict geometric problem. If we don't know the underlying shape of a distribution, how do we rigorously measure and define the distribution of its points? Expectation anchors the system. To map the behavior of the data, we need a mathematical metric that strictly quantifies volatility. This is the second moment. We define the variance as the expected value of the squared difference from the mean. We write this as sigma squared. Its positive square root, sigma, is what we call the standard deviation. Notice the specific algebraic choice here. We take the distance between our variable and the mean, x minus mu, and we square it. But why is that specific operation necessary? First, it forces all deviations to become strictly positive. If we didn't do this, negative distances on the left would cancel out positive distances on the right, falsely implying a spread of 0. We could just take the absolute value of the distance, but absolute values create sharp, non-differentiable corners in calculus. Squaring creates a smooth polynomial, which gives us the rigorous differentiability required for advanced mathematical proofs. This choice creates a specific mathematical weight. Squaring disproportionately punishes points falling further from the mean. A point 2 units away contributes 4 times the variance. A point 3 units away contributes a massive 9. Variance is an aggressive metric. It is explicitly designed to penalize extreme deviations, giving us the exact groundwork needed to establish absolute probabilistic bounds. This penalty guarantees probability containment, Chebyshev's inequality. We derive it directly from the variance. Take an unknown probability distribution. We define an extreme tail boundary at a distance lambda standard deviations from the mean, mu minus lambda sigma, and mu plus lambda sigma. The total expected variance over this entire curve is strictly greater than or equal to the variance isolated just within these extreme tails. Inside the tails, the minimum distance to the mean is lambda sigma. Substituting this defines a lower bound. Variance is greater than or equal to lambda squared times sigma squared times tail probability. Dividing both sides isolates the probability, proving Chebyshev's inequality. Chebyshev's inequality is an absolute containment field. It caps the probability mass far from the center, completely agnostic to the underlying shape of the distribution. At first glance, 1 over lambda squared is a remarkably weak polynomial bound. Why do we rely on it when much stronger bounds exist? Because of pathological cases. You can construct a discrete distribution where a probability mass of exactly 1 over 2 lambda squared sits perfectly at the extreme boundaries, and the rest sits dead center at the mean. Here, Chebyshev is perfectly tight. It cannot be improved. Compare that worst-case scenario to the standard normal distribution. Its extreme tail probability is calculated by an integral that resolves into an exponentially decaying asymptotic form. The normal bound shrinks exponentially fast, while the Chebyshev bound shrinks at a slow polynomial crawl. The second moment method demands this weaker Chebyshev bound because it guarantees containment. It holds firm in worst-case, unknown environments where normal distributions completely fail. Until now, we have treated our random variable as a single, isolated entity. But real probability deals with massive, interconnected systems. We fracture variable x into microscopic atomic variables, giving a macrovariance equation. Total variance equals the sum of individual variances plus their covariance interactions. We map this in a structural matrix. The main diagonal isolates individual variances, while off-diagonal spaces map the covariances. If two variables act completely independently, the expected value of their product strictly equals the product of their expectations. The terms cancel. Their covariance collapses to 0. The macro volatility of any complex universe is entirely dictated by its atomic parts and the microscopic mathematical dependencies between them. We can simplify the structure further by using indicator variables. These hold binary states. They equal exactly 1 with probability pi and 0 otherwise. For an atomic indicator variable, the exact variance is simply pi times 1 minus pi. Because probability is a fraction, multiplying it strictly reduces its value. This creates a rigid rule. Variance can never exceed expected value. Substituting this atomic rule back yields our ultimate boundary. Total variance is less than or equal to expectation plus the sum of covariances. Reducing complex events into binary indicators creates a highly scalable algebraic framework. It gives us the absolute power to bound unimaginably complex probabilistic systems. We've built our framework on a purely abstract probabilistic foundation using 0 fixed data. Yet these methods can analyze deterministic sequences. By treating fixed numbers as a random sample, we apply this second moment method to uncover the distribution of prime factors. We will apply this tool to the primes, using pure randomness to prove a fundamental law about the most rigid structure in mathematics.